Okay, so let's say we've got, this is supposed to be a straight line, okay? And, okay, so let's do 20, 30, 40, 50, 60, 70, okay. All right, and then, let me fix this one up. Just I'm going to just draw lines to kind of indicate where these things are supposed to be going. Okay, so these are is that visible? Okay, all right, and then so this will be age of employees at company A and B. Okay, so we'll just say, all right, 1. All right, what is the IQR of ages at company A? What about company B? Max age of employee at A, and then what about at B? Okay, and then we'll say 3. What is the difference in median ages? Okay, take like 2 minutes. I feel like it shouldn't even take that long. 1 minute to answer these. And some of these you're going to just have to kind of ballpark the answers, just because this is not exactly precision straight lines. Are we good? We need another minute? Okay, thank you for your enthusiastic responses. All right, IQR of the ages at company A, what do we say? So we just have to kind of ballpark what this number is and what this number is. Okay, so this looks like it's what, 35? And this looks like what, 21, 22, something around there? Okay, so whatever your answer is there. So your answer is going to be what, 13 or 14? 13 or 14, something like that, right? So 35 minus 22, 35 minus 21 would give us 13 or 14. Okay, IQR at company B, Q1 is what? 30, okay, and Q3 looks like what, 48, 49, something around there, 48, 49, so your answer there is going to be 18 or 19. Is that okay? And then if somebody said which company has a greater spread in ages using the IQR as a measure, we would say company B has a greater spread in ages, right? Company B might be your traditional company that's been around for a long time, like, I don't know, General Electric or something like that, okay? Whereas company A might be like a startup, which generally skew younger, okay? What's the max age of employees at company A? Like 49, something around there, okay? Max age of employees at company B? Looks like 65. Okay, difference in median ages. Okay, I don't know what this is. What, 27, 28, something around there. And right here it looks like 40. Okay, so we would say 12 or 13. Okay, is that good? What is this chunk right here? What percentage of employees at company are between 20 and 22 years of age? 25%, okay? So this little bit, this is like 1/4 of the company is between 20 and 22 years of age, okay? So 25% of employees. I should have probably brought this down to 18. Okay, so I'm not sure what kind of company this is. Maybe they operate like a call center or something. People right out of high school, put them down on a phone, give them their money back if the customer's angry, things like that, right? Minimal training jobs. Okay, we feel good about this? All right, we'll keep moving on. So now we're going to start a new chapter. We're going to start chapter 4. Okay. So we are still kind of in this realm of describing our data. So last week, on Wednesday, when we covered chapter 3, we were talking about describing a distribution of data. All right, and we learned how to describe the distribution, and the distribution is just kind of the idea of when we look at the values that we see. For example, when we were talking about the distribution of ages at a company, we could say things like the average age at company A, the median age was 27, and the median age at company B is 40, or something like that, right? And we can use descriptive words to just describe where the middle is. We have words to describe the IQR or the spread. And so you say at company B, the spread is 18 or 19 years for the IQR and things like that. And then we have graphic displays, and this gives us a sense of how the numbers or how the values are distributed at these two companies or something like that. Okay, today we're still describing our data, except now we are going to look at describing two numeric variables, okay? So we're going to describe the relationship between two numeric variables, all right? This is different from describing one numeric variable for two samples, okay, which is what we did on the previous slide. On the previous slide, where I showed company A and company B, it was the same numeric variable. It was one numeric variable, the age of employees, but for two samples. Today, we're going to talk about just looking at one sample, and within that one sample, we're looking at two variables, okay? Okay, so we had, so today it's going to be, one sample. I mean, maybe more than one sample. One sample, but two variables for the same sample. Okay, and so here's just kind of a silly example, and let's just say you decide to study a particular species of snake. Okay, and I'm gonna this is this is what a snake looks like. All right, there you go. So there's a snake, all right, and this is the extent of my art abilities. Okay, and all right, and here's another snake, all right. Okay, and we want to know, is there a relationship between the length of a snake and the weight of a snake? Does anyone, I don't know anything about snakes. Do snakes just grow more bones in their body when they get longer? Is that how it works? Or do they all have the same number of bones and the bones just get longer? I don't know, okay. That would be another question. Is there a relationship between the number of bones and the length of a snake? I don't know, right? Because there's something like giraffes have the same number of neck bones as a human, right? I think. Is that a fact that I'm just making up? I think it's something similar, right? That the giraffe has the same number of neck bones, it's just that their neck bones are longer, obviously. Okay. So is there a relationship between the length of a snake and its weight? Okay, and what do you guys think? Yes, right? Generally, if we're looking at the same species of snake, if you got a longer snake, we would expect it to weigh more than a shorter snake, okay? And likewise, if you went the other way around, and if you just weighed the snakes, and this snake weighs a little and this snake weighs more, you would expect the heavier snake to be a longer snake, right? If they were coiled up and you didn't, I don't know, okay? So is there a relationship between the length of a snake and its weight? And the answer is going to be yes. We expect longer snakes to weigh more than shorter snakes. Okay, and this is pretty much what we're going to talk about today. This will be the focus of today's lecture. Is just we want to be able to describe the relationship between two variables. In this case, we're describing the relationship between length and weight, okay? Except we want to be a little bit more precise in our language. Just like last week when we were talking about describing a distribution, we didn't want to say DMV, there's lots of spread. DMV room, there's lots of spread. In the second grade classroom, there's very little spread in ages. Okay, we had values to describe, the exact standard deviation and the standard deviation. And similarly, when we talk about describing the relationship between two variables, yeah, we can say things like longer snakes will tend to weigh more than shorter snakes, okay? But we want to give a little bit more precision to this language, okay? We can say the correlation between length and weight is 0.8, okay? Versus, for snakes, maybe the correlation between length and weight is like 0.9, and for humans, the correlation between height and weight is 0.6 or something like that, okay? We can describe how these things are related using a little bit more of a precise language. And we can also later come up with an equation to describe the relationship. We can say if one snake is 1 inch longer than another snake, we would expect the longer snake to weigh about, 15 grams more than the shorter snake, okay? We expect, but we want to be able to describe that exact kind of relationship as well. And so that's what we're going to focus on today. Okay, we're just going to talk about describing the relationship between two numeric variables, but we're going to learn kind of the precise language. Okay, so I'll just write big picture for today. Okay, so learn kind of the more precise descriptors for a relationship. To numeric variables. Okay, so kind of the first tool that we have is the Scatterplot. This is a graphic display, and it's basically you're just plotting coordinate pairs. All right, so for example, let's say we gather a table, okay? So this is our table, and we've got, snake 1, and we've gathered some variables. All right, and one of the variables will be the length, and the other will be the weight. And I'm just making up numbers here. I have no idea, okay? So maybe this is in inches and this is in ounces. I don't know. Okay. And then we've got snake 2, snake 3, snake 4. Okay. Snake 2 is 14 inches long. I don't know, weighs 16 ounces, 10 inches, and 10 ounces. 8 inches, 9 ounces, I don't know. Okay, et cetera, et cetera, et cetera. Okay, so there's, just assume, more data here. Okay, and then so your scatter plot is you're just basically plotting x and y coordinates. So I'm going to do 7, 8, 9. Okay, and then there's 8, 10. Okay, and you just go through and you plot each of these pairs. So you go 12 and 14, and we get a dot right there, and then 14 and 16, and we get a dot, I don't know, right there, and 10 and 10 puts a dot here, and 8 and 9 puts a dot here. Okay. length, and weight. Okay, and so we can look at this and we can say, all right, sure enough, at least for our data points, the longer snakes tend to weigh more than the shorter snakes. Okay, and as we learn to describe the relationship between two numeric variables, I would say there are kind of three things to mention. So three aspects that are important to describe. Okay, and so one will be the shape of the relationship. And we'll say, and so this is going to be either linear versus nonlinear, okay, as far as this class goes. We've got the direction of the relationship. And the strength of the relationship. Okay, so the direction will be, positive, negative, neither. And strength will be strong, weak, something in between, moderate. Okay, and I'd say those are the three aspects that are important to describe. If there's anything highly unusual, that's also important to describe, okay? And then if there's something highly unusual, be sure to point that out. Okay. All right, so we'll start off with describing the shape. Okay, linear versus nonlinear. All right, so the shape, okay, so linear means a straight line can summarize the relationship. Okay, so something like, okay, of course, we might expect there to be some scatter, but overall, seems like a straight line, something like that, okay? Okay, so both of these would be linear. That's what we got. Overall, looks like a straight line. Okay, and then everything else, if a straight line doesn't work, okay, then we would put that under the realm of not linear. Okay. Nonlinear, basically not a straight line. All right, yeah, as far as this class goes, I mean, if you were to take another statistics course, then, maybe you would use more specific words for the nonlinear relationships, okay? Okay, so this is like temperature throughout the day, gets hotter the day, cools off at night, hotter the next day, I don't know. Stuff like that, right? So anything where the straight line's not going to work. Okay. And of course, all of these we would probably experience some scatter as well. Something like that. Okay, so these are all nonlinear. Now, the only way you can really tell if something is linear versus nonlinear is by plotting it. Okay, so you have to create a scatter plot, and this is really the only reliable way to decide if something is linear or not. Now, we don't, I shouldn't say we don't, these don't exist, but generally your eyes are going to be your best tool or best thing to decide if a relationship, if a scatter plot looks linear or not. Somehow our eyes and our brain is trained to really be able to recognize patterns and stuff. That's why we can look at the stars, although maybe not in LA, but if you look up at the night sky, you can see you see patterns and shapes, and you know, when you see like Orion's belt, you're like, oh, that looks like a line. Our eyes are really good at recognizing patterns like that. And so so it seems a little weak to just say, how can you tell something's linear? Make a plot and look at it, but really that's the best way. There are advanced statistical tests to kind of test the linearity of something, but really they don't really beat your eyes. Okay, so to decide if something is linear, you have to graph it. Okay. You must graph it and look. Okay. And it's true that two people could look at the same graph and one person says, this looks linear, and the other person says, I'm not so sure. And that's fine, and it probably means it's something in between, okay? But if you look at it and you go, that's definitely not linear, then it's not going to be linear. And if you look at something and you go, oh, that looks pretty linear, then that's fine, okay? So that's linear. All right, the other part is the direction of a relationship. Okay, so we got direction and strength. All right, so the direction of a relationship, we've got positive. Okay, and positive means large values of x tend to go. So if one variable is x and the other variable is y, you'd say large values of x tend to go with large values of y. And small x, I'm going to just do arrows, go with small y. Okay, and this is like tends to go with, right? And so if this is my x-axis and this is my y-axis, this side would be large x, and this side would be small x, and down here would be small y, and up here would be large y, right? Okay, so large values of x tend to go with large values of y, and small values of x tend to go with small values of y. And kind of this relationship generally holds. And so a positive trend basically has something like this. Large x goes with large y, small x goes with small y, and you have this overall direction that looks like that. Okay. The negative relationship is kind of the opposite. So negative would be something like large X tends to go with small y, and small x goes with large y. Okay, so again, this is large X over here, and over here is small x, and down here is small y, and up here is large y. And what we have is small x goes with large y, and large X goes with small y, and your relationship looks something like this, okay? So small x goes with large y, large X goes with small y, and the overall trend goes that way, the direction there. Okay. So maybe just silently sit there and think of a data set where you have two numeric variables, and think of two variables that have a positive relationship, and try to think of two variables that have a negative relationship, maybe for a different data set. Okay? You don't have to shout them out or anything, just kind of think, see if you can imagine something. And I'll just give you some examples in a moment here. Okay? So try to think of something that might have a large X, large Y positive relationship or not. Okay, I'll give you some example here. Okay, so an example would be snake length and snake weight. All right, so when we were talking about the snakes earlier, we expect the longer snakes, the larger snakes, snakes with high length to have high weight, snakes with low length to have low weight, okay? Any other examples for positive relationships? Anyone brave enough? Yeah.
Increase, recreational marijuana shops and increase usage of recreational marijuana.
Okay, so greater usage. Okay, so maybe, okay, we'll just say usage and number of shops, okay? And this is probably true for any product, whether it be recreational marijuana or car dealerships and horse sellers, right? If there are places where there are a lot of people using marijuana recreationally, there's going to be more shops, right? And if there's a place where there's lots of people riding horses, there's probably going to be more horse dealers. I don't know, okay? I guess maybe not a place, but a time, right? So if we rewind the clock and go back to, when did they ride horses? 1888? I don't know, okay? We would see more horse riders and horse dealers, if that's what they were called. Stable people, something. All right. Okay, and then in places where there's very little recreational marijuana use, we're going to see very few shops and things like that. Yes. Okay. So probably we'll do usage of product, whatever product we are talking about, and merchants of the product. Okay. Whatever that is, right? Like the Apple Store, right? You guys weren't alive, but in 1999, nobody used an Apple product, okay? I wouldn't say nobody, but very few. And there weren't very many Apple stores, okay? If there was even an Apple store, okay. But anyway, and today, you see them everywhere, okay. Okay, and then negative relationship example could be something like car mileage for like a used car, the vehicle mileage versus sale price. Okay, we'll say for one particular model. All right, so let's say you're set on buying a used Honda Civic or something like that, okay? And you say, well, there's different factors that go into how much you're going to pay for your used car, but mileage is going to be one of them. And in general, if the car has more mileage, it's going to sell at a lower price than a car that has less mileage. Okay, things like that. Any other examples for negative relationships? Yeah. Newspaper sales over time. Yeah, okay. So as time has progressed, sales of papers have gone down. Yeah, okay. All right. Or maybe even also just paper usage, newspaper usage versus digital readership or something, right? Like that. If you go to the newspaper company and you say, well, how many digital subscribers do you have versus how many paper subscribers you have? Probably a negative relationship, I would assume, that as one goes up, the other goes down, something kind of a vice versa. Okay, and then I'll put in neither positive nor negative. All right. Okay, so something like this. X versus Y, this is neither positive nor negative. I don't know, something like X is money in the bank, how much money in your bank account. And Y will be something like your shoe size, okay? And we would not expect to see a relationship there. There are people with lots of money and little feet, lots of money with big feet, people with little money with little feet, and little money with big feet, things like that, okay? I don't know, other things where there's just a big mess, okay, of things. This would all be neither positive nor negative. You could have something like this. I don't know, and this would be like time since rocket launch versus altitude or something, okay? Altitude of toy rocket. Okay, so those are neither positive nor negative. Okay, and then the third aspect of describing a relationship will be the strength of a relationship. Okay. And when we talk about the strength of a relationship, what we're talking about is how well can you use one thing to kind of predict the other thing, right? Or, how much does one variable, like how much information does it give you about the other variable, okay? So we can think of this loosely as how well can we predict the other variable based on one variable. Okay. Okay, and so a strong relationship would be, what we would see is that one variable helps us can make good predictions about the other variable, okay? So one variable can help us make good predictions about the other variable. Okay, versus, and what we would also see is there would be little scatter around kind of a trend line. Versus a weak relationship, we would see, you know, one variable can improve our predictions about the other, but not very much, okay? Our predictions about the other variable but not by much. Okay, and then what we would see is lots of scatter. Okay, so just kind of if you see something like this, so there's just a tiny bit of scatter here. Okay. And so we would say this is a strong relationship. And the idea here is this is like if we're given this x value. Okay, so if we're given this x value, we would come up here and all of our predictions would kind of be within inside this little window here, right? This would be, we predict y to be in this small window. Okay, so we can make a pretty precise prediction for y given a particular value of x. Okay, and on the other hand, for a weak relationship between x and y, we'd see, you know, a lot more scatter. Something like this, okay? And so we'll say, if we're given this value, given this x value, all right, so we would fit our trend line, whatever that looks like, something like this, okay? And as far as, maybe I'll use a different color, kind of my window of prediction would be somewhere is going to be kind of in between is going to be somewhere like that, okay? Our prediction for y is in a much wider range, okay? Does that kind of work? For strong and weak relationships. Okay, and so, if you're dealing with people, most of your predictive power is going to be fairly weak, okay? So you might see relationships between number of years of education and annual income, okay? But the relationship's not going to be super, super strong because people who have, only a few years of education, in general, will earn less than those who've had a lot more years of education. But even within, people who have PhDs and graduate degrees, there's going to be a huge range of incomes. And then people who have just a high school degree or something like that, a high school diploma, there's still going to be a large range of incomes there, okay? And so, how much does one thing help you predict the other? Something like years of education and annual income, it's difficult to say, right? On the other hand, if you're talking about a physical or chemical process or something where there's not a whole lot of people involved or something, and it's just kind of like, if I use this much, if you're thinking of some kind of chemical reaction where you're going to say, how much ingredients do I put in over here? How much of this thing do I have, and how much product does it produce? We're going to get, I think you're going to be able to make very good predictions. Now, because of just different factors, you can have, put in 1 pound of ingredient, and it might produce just ever so slightly different amounts of product, okay? But the amount of, how well you can predict, you're probably going to be within a couple grams or a couple ounces of other things if you're using the same amount of product, right? So if you put in 1 pound of, whatever chemical this is, and maybe a pound is a lot, okay? But if you're putting in the same quantity, you're going to expect to get something around the same output, maybe a little bit more, a little bit less, just because of different factors there, but you can make pretty good predictions. Whereas if you take 2 people and you say this person has 16 years of education and this person has 16 years of education, predict how much income they have, there's going to be a lot more range in terms of the other variable there. Okay? So, so if we're talking about something like snake length and snake weight, we would say something like the relationship between snake length and snake weight is linear, is positive, and fairly strong, okay? Whereas, other aspects, maybe it's not going to be linear, maybe it's going to have a positive or negative relationship, maybe strong or weak, okay? And just like we had a numeric value to describe the spread, things like the standard deviation, the IQR, we have a numeric value, a numeric summary, okay, called the correlation. Okay, technically the full name is the correlation coefficient. Okay, correlation coefficient, but we often just call it correlation. So I'll put coefficient in parentheses. The correlation coefficient is a numeric value that basically summarizes the direction and strength of a linear relationship. Okay. And the symbol is R, okay? R like relationship. Okay. Technically, the correlation is just the result of a formula, okay? And so it can be calculated for any 2 numeric variables in the same data set. but it really only makes sense as far as interpretation goes if the relationship is linear. Okay, so the value only makes sense for linear relationships. Okay. And how do we tell if two variables have a linear relationship or not? What's the best way to tell if two variables have a linear relationship? Okay, and your answer is? What's that? Your eyes. Exactly. Good. Thank you. Thank you for responding. So we must make a graph. And use our eyes to see if it is linear. Okay. All right, so rules about correlation. All right, so we have the correlation is always a value between -1 and 1. Okay? And again, assuming if it's linear, okay, if R is, I'll say the sign of R is the direction of the relationship. Okay, so if R is positive, the direction is positive. If R is negative, the direction is negative. Okay, and then kind of the magnitude of R is the strength of the relationship. So if R is far from 0, meaning it's close to 1 or close to -1, the relationship is strong. And if R is close to 0, the relationship is weak. R is far from 0, so close to 1 or close to -1. Relationship is strong. And if R is close to 0, relationship is weak. Okay. And again, R does not tell us, R by itself will not tell us if the relationship is linear. Okay, I guess with the exception of R being exactly equal to 1 or exactly equal to -1, but I think that's beside the point. Okay, R by itself will not tell us if the relationship is linear. So I'm going to just cheat and use examples from the textbook. That show us, and we'll find out what page this is on. Okay, so here are some different scatter plots that show us the values of R, okay? And I guess they're corresponding values of R. So you can just, this is in section 4.2 of the textbook, okay? Okay, so here we've got R equal to 1.0. And if we look, we can see that the graph is perfectly in a straight line, okay, that the dots are in a perfect straight line. There's no scatter, so you have R equal to 1.0, okay? No scatter, perfect straight line. Oops. No scatter, positive relationship, okay? And as the, and so here we've got a little bit of scatter, okay? So just a little scatter. And still a positive relationship. This is life expectancy for men and life expectancy for women across different countries, okay? And so here's a country where the life expectancy, mean life expectancy for men is like 80, and the mean life expectancy for women is like 85 or something. Over here, the mean life expectancy for men is 60, and the mean life expectancy for women is either 60, 62, 68, or 70 or something like that, okay? And so given if we, and over down here, the life expectancy for men is like 40 and the life expectancy for women is 41 or something like that. So if we know the life expectancy for men in the country, we can make a pretty good prediction for the life expectancy for women in the country. But even though you have two countries with the same life expectancy for men, the life expectancy for women might be different by a little bit, right? Over here, you got, if you have two countries where the life expectancy for men is 70, one might have a life expectancy for women of 72, and the other might have a life expectancy of 74. So there's a little bit of scatter. You can't make a perfect prediction, but it gives you quite a bit of information, okay? Here's height and weight, the relationship between height and weight in a bunch of different, I'm assuming, people. And so, you know, you got some more scatter, and then here is a lot more scatter and things like that. And we can see that the correlation coefficient for each of these things, the R value keeps decreasing as the amount of scatter increases, okay? Until we get to this point where there's now no relationship between, I don't know what age and time is, okay? But there's a relationship where the correlation is 0 here, okay? And then as we continue, here we have negative relationships, okay? Until we get to a straight line negative relationship. Maybe I can just, so these are a bunch of negative relationships, and you don't have to copy these pictures. I mean, you can redraw them in your notebook if you want, but they're available in your textbook, and I'm just going to copy them right here into the notes. Okay, and then so we get negative relationships, okay? And so here, R is 0, and here we have R negative 1 to no scatter, and this is a bit of scatter to, you know, more scatter, and these are all negative relationships. Is this okay? All right, so here's a question. Let me just put some dots here. Okay, and we'll assume that, you know, x is on, these are kind of on the same scale. So we'll say this goes from 0 to 10, and this also goes from 0 to 10, and 5, and this goes from, we'll say 0 to 10, and this also goes from 0 to 10 up here. And so this probably ranges from, so kind of the smallest value here is going to be like 1, 2, 3, 4, maybe on the range from like 2 to 5, 3 to 5, and this goes pretty much from 0 to 10 and things like that. Okay, so the question is, which one has a greater correlation? Okay, so we'll say this is Scatterplot A versus Scatterplot B. Which plot has the larger correlation? Larger value of R. Okay, and what's your answer? Anybody willing to answer this one? Which one has a, which scatter plot has a greater correlation? Okay, answer? Yeah.
Is it the same?
It's the same. That's exactly right. So which scatter plot has a larger correlation? Neither, okay? Scatterplot A and scatterplot B both have a correlation of 1.0, okay? So both have R equal to positive 1.00 because the dots are exactly on the line. They, there's no scatter around the trend line, and so both have a correlation of 1. So one thing is that correlation does not tell us anything about the slope, okay? If I ask you which plot has a steeper slope, you would all say A has a steeper slope, right? You would say that, I think that's easy to see, right? So, you know, because they're on the same scale. Plot A has a steeper slope, has a, you know, larger slope than plot B. Okay, but scatter plot, but correlation has nothing to do with slope. Okay, it only tells us about the amount of strength. Is the strength strong or weak, positive or negative? Okay. And just draw one more. Okay. What if I throw in this? Okay, so this is a flat line. Okay. So in this plot, what is the correlation? This is a flat line. What's the correlation in this in this plot? And you guys tell me what? 1. The answer is actually 0, okay? Because it's neither positive nor negative, right? It's a little bit tricky. I purposely did this to kind of trick you guys up. So it's absolutely true that this one has a correlation of 1. Plot A has a correlation of 1. Plot B has a correlation of 1, okay? But there's still a tiny bit of slope in B. But as soon as the line becomes flat, the correlation becomes 0, okay? Because the relationship is neither positive nor negative. We can still say in plot B that larger values of x go with larger values of y, and smaller values of x go with smaller values of y. That's still true. But as soon as the line becomes flat, it's no longer true that larger values of x go with larger values of y, or smaller values of y, because they're all the same value of y. Okay? This could be something like, I don't know, x could be GPA, and y could be number of fingers. Right? And depending on your data set, okay, if you don't have a very large data set, okay, chances are every single person in your data set will have 10 fingers, okay? Now if you increase your data set to, you know, be larger than a couple hundred people, then you might encounter somebody who doesn't have 10 fingers. But if you have a fairly small data set, okay, probably everyone in that data set will have 10 fingers, but everyone will not have the same GPA, okay? And so, can you make perfect predictions? Yes, but does one variable really tell you much about the other? It doesn't. And if we tried to flip it the other way around, where we tried to predict GPA based on number of fingers, we certainly cannot make any kind of good prediction about GPA based on the number of fingers that you have, okay? And so, so in this case, the correlation between GPA and number of fingers is 0. Which actually brings us to another point, in that the correlation between x and y is going to be the same as the correlation between y and x, okay? So I'm going to just kind of list off some key ideas, key properties of R. Okay. All right, so number 1, the order of variables about, the order of variables does not affect R. Okay, so correlation between x and y is the same as the correlation between y and x. Okay, so let's, I don't know, this is a silly example. Okay. But it's true, all right? And I don't want anybody to, I hope I don't offend anybody, but let's say, I think one of those online dating platforms released some data about their customers and stuff like that. It's like Match.com or OkCupid or something, okay? So they released some data, and then people were like analyzing this data. And so this was for kind of straight, as far as orientation goes, for straight customers, all right? Let's say X was the height of a male, and y was the height of the female. Okay, so here's the question. Does the height of the male, will that tell us anything about the height of the female with which they formed a match? What do you guys think? Yes, no? If we know about how tall the male customer is and they matched with a female, can we predict anything about the height of the female? What do you think? Okay, yes, no, maybe. All right. So think about your answer there. Okay. What if I flip it the other way around? Height of the female versus height of the male. Okay. If we know something about the female's height, and we know that they matched with another customer on this online website or whatever it is, okay, can we predict anything about the height of the male? Okay, so no, this class, nobody's like shouting out any answers, which is fine. But a lot of times when I post the first question and I say, if we know the height of the male, can we predict anything about the height of the female? The general trend is probably like, nah, not really, okay? But then if I flip it around and I say, if we know the height of the female, can we predict something about the height of the male? Then suddenly people start to say, oh, well, maybe, okay? Maybe we can start nodding their head, okay? Well, the thing is the order of the relationship doesn't matter. So if we are able to predict the height of the male based on the height of the female, then certainly the reverse is also true. If we can predict the height of the male, we can predict the height of the female. And you know, general trend shows that if the female is taller than average, the males that she will match with will be taller than average. And similarly, the data also shows that if the male height is lower than average, in general, the height of the female will also be lower than average, and things like that. And so there is a relationship that appears in the data here regarding the height of customers on an online dating website. Okay. So, but the order of variables does not affect R there, okay? Another thing, okay, multiplying by a constant or adding a constant to all values will not affect the correlation. Okay, so practically speaking, this just generally means if you change the units, that's not going to affect the correlation. So if you decide to change from measuring in inches to measuring in centimeters, that's not going to affect the correlation, okay? Or if you measure temperature in Celsius versus temperature in Fahrenheit, which involves addition and multiplication and things like that, changing units does not affect correlation, okay? I should say multiplying by a positive constant. Okay, obviously if you multiply it by a negative constant, it's going to flip all the numbers around. So as long as you're multiplying it by a positive, non-zero constant, it will not affect the correlation. Okay, again, R only makes sense for linear relationships. And can be greatly affected by outliers. So let me give us a couple of examples here. Okay, so earlier what did I say? Money in the bank and shoe size, right? Okay, so money in the bank is X and shoe size will be Y, all right? And so in general, we would expect the correlation to be 0, yeah? So we graph our data. So you got people with big feet, people with small feet. Okay, and people have different amounts of money. Okay, so for a regular sample of data, and regular in quotes because I don't know what that means, but regular sample of data, R is equal to 0 or very close to it. Okay. All right. What if Shaquille O'Neal ended up in our random sample here? Okay. So Shaquille O'Neal, former NBA player, and now he does commentary on TNT. Okay, he has lots of money, very successful entrepreneur. I think he owns like a bunch of hamburger restaurants, Five Guys, and things like that. Anyway, it makes money from doing TV and stuff. Also known for having extremely big feet. Okay, and so he would be, I don't know where his bank account would be, but he, let's just throw him up here. Okay, so this is Shaquille O'Neal. All right, and so if we include this, our trend will suddenly go from having no trend whatsoever. Okay, so this would be R is 0 to suddenly we're trying to kind of accommodate the existence of this outlier, right? And then we would have this interpretation that shoe size and income or bank money that you have, wealth, are somehow related, which is obviously, I don't know about obviously, but should not be true, okay? Okay. And I guess sample of data for adults, okay? If we included children, then we would see a positive relationship because kids will have small feet and very little money in general. And then so suddenly they would throw off our analysis, right? Okay. And then again, kind of the warnings, once again, the warning is that correlation itself does not tell us if it is linear, if the relationship is linear. Okay, and so you have, there's something known as Anscombe's quartet. Okay, and let me look at this. Okay, so here is, I'm going to copy this plot. Can that work? Copy image. I'll put this right here. Okay, so all four plots have the same correlation of something. 0.8, I think. 0.816. Let me see. So you can look this up. Okay, yeah. So all four plots have the same mean, have the same variance for x and y, and the same correlation of 0.816. Okay? So all four plots have r equal to 0.816. Now, really, it only makes sense, okay? So correlation only makes sense for this plot. Okay, but here, this is nonlinear. Here, it probably should be a straight line, but you've got one outlier, right? Should have a straight line with r equal to 1, but the outlier throws it off. And then over here, pretty much almost all data is at x equal to 7, and then you have the entire trend based on basically one observation. Okay, so this last plot down here, let me just switch over to the Wikipedia page. Okay, so for this last one, pretty much everyone's observed around here, and then you've got one unusual observation. This would be kind of like, this is not the example, but it would be like you interviewed a bunch of people and you said, how many fingers do you have, and how much money do you have? And you get a whole bunch of people with 10 fingers, and they have varying amounts of money. And maybe you encounter someone who happens to have an 11th finger, okay? And you encounter this one person with an 11th finger, and somehow this person was very successful and made millions of dollars, okay? And then so if you establish a trend based on that, where everyone has the same value and there's only one value that's different than everyone else, then suddenly it appears that there's correlation, okay? And obviously that's not a good, that doesn't make sense, okay? It doesn't make sense to try to establish a trend based on one observation. Stuff like that happens in real life and in business and things like that. People will say like, we gathered, and we kind of do this in our personal lives too, right? Like you encounter a whole bunch of people, okay? And then you meet one foreigner from a country, and this is the only person you've ever met from that one country, and they do something unusual. And in your brain, part of you asks, are all people from this country? Do they all do this unusual thing? And you go, well, I shouldn't think this. But this is often, how we interact with people. We say, this is the only representative in my life experience of, this thing that I'm not familiar with, right? And we might try to draw conclusions or trends based on that, okay? And so, doing something like this is risky, and similarly, not plotting your data and assuming that the correlation tells us information is also a risky thing. So you have to kind of plot it and just say, oh, in the context of this is really the only observation that we have out here. It doesn't make sense to draw a conclusion for this. All right, is that good? Okay, let's see. I got about a little under 20 minutes. And so the last part that we're going to cover today is finally being able to create an equation to describe these relationships, okay? And this part is called linear regression. Okay? And in linear regression, what we want to do is we want to create a mathematical model, or in our case, a simple equation to describe the relationship between two numeric variables. Okay, so instead of saying longer snakes tend to weigh more than shorter snakes, okay, we want to say, if one snake is 1 inch longer than another snake, we expect, on average, that it will weigh, 0.8 ounces more than the other snake. Something like that, okay? So we can be a little bit more precise in our description. We can say 1 extra inch means our prediction on average goes up by 0.8 ounces. Now, of course, when we compare two snakes in real life, they're not necessarily going to have this exact relationship, right? You might have a 15-inch snake and a 16-inch snake that weigh exactly the same amount, okay? That's certainly possible. It's also possible that the longer snake weighs less than the shorter snake because maybe the shorter snake just had a meal or whatever, okay? So as far as individuals go, we can't make any kind of true predictions. But overall, if we just said if we compared all the 16-inch snakes and averaged them, compared all the 15-inch snakes and averaged them, we can make these kinds of trends, right? And I think this was one of our big idea points from in the big picture thing. We said we can only make conclusions about populations, and we can only make predictions about what happens on average, okay? It's nearly impossible to make predictions about an individual observation. So if we're talking about an individual snake, an individual person, it's really hard to make a prediction about that one person. But on average, if we just say on average, snakes that are 16 inches long, on average, we expect them to weigh 0.8 ounces more than snakes that are 15 inches long, okay? All right, so anyway, this is what we want to get to, all right? So we want to be able to say something like this, and to do this, right, this will come down in the form of a linear equation, okay? So we will write a linear equation, all right? And so a linear equation needs, okay, so we need a slope and an intercept. Okay. And different textbooks use different letters to represent what the slope and the intercept is. Our textbook uses intercept is A and slope is B, okay? And we write y hat is equal to A plus B times X, okay? So y hat, this is pronounced y hat, and this is our prediction for y. And we put the hat over it to distinguish it from the actual value of y, okay? Okay, our prediction for the variable y, A is our intercept, and B is the slope, okay? And then X is basically the X variable. And I don't want to get into this, but I'll just kind of throw this up here. You can search for explained visually least squares. And this, I don't know if you've heard the term, for least squares regression, okay, but the first hit will be ordinary least squares regression, and it talks about, you know, when we fit a line to our data, how do we decide what is our best fitting line? It's going to be the line that minimizes what we call the squared residual, and so here, for this dot here, this is the actual data point, and it has, you know, a value of like 84 or something. And currently, our line says if the value is at 84, we predict 84. Okay, and so the actual value is maybe like 65, and so it has a difference between what the line predicts and what the actual value is, and that's the difference. This vertical distance between the dot and the line. Okay, and what we're doing is we square that distance and we get a square. And if I adjust the slope here, okay, the line gets steeper, and we can see that the difference between the line and the dot remains stationary, but the difference between the line and the dot gets bigger, and the squared difference, what we call the squared residual, gets bigger and smaller. And if I adjust it so that the line is very close to it, then our square becomes a lot smaller, okay? But as I adjust the slope, it changes the size of the other squares, right? So I can make the square for the brown dot small, but it makes the square for the green dot bigger, okay? So I can kind of adjust this, and I want to kind of adjust this in such a way that the total squares are as small as possible, okay? So explained visually, least squares. You can search Google for that, and the idea is in least squares regression, tries to minimize the total area of squares, right? Okay, and the squares are determined by what the line predicts and the actual value. Okay, so this, here's the actual value. And this right here is what the line predicts for that x. Okay, this is if you're interested in how it works. We can just, if you're not, you can kind of skip over this, but I wanted to throw that in there. So anyway, just going back to it, we've got y hat is equal to a plus bx, okay? And the best fitting line will always have these properties. Okay, and you know, these were determined by calculus. We don't have to worry about it, okay? We don't have to, you don't have to worry about the derivation of this. Unless you decide to major in statistics or something, then you have to worry about the derivation. But here we can always just say, for the intro stats class, we're just going to say the slope is going to be r times sy divided by sx, and the intercept is going to be y bar minus b times x bar. Okay, so r is the correlation, sy is the standard deviation of the values of y, okay, and sx is the standard deviation of the values of x, okay. Y bar is the mean of y, and x bar is the mean of x. Okay, and because the intercept uses b as part of its equation, you need to find the slope first. Okay. I'm probably going to run out of time before I can finish all of this stuff. So let me just kind of do an example here. Okay, so what we're going to do is, so the example is, I guess we've got books on a bookshelf. All right. So this is some book, and we're going to measure the width of the book, okay? This is going to be our y variable. The y variable is the width, and we're also going to count the pages, and that will be x. Okay? And we want to predict the width of the book based on how many pages are in it. Okay. All right, and so we would expect books with more pages will be wider, and books with fewer pages will be thinner, right? So things like, I don't know, those Game of Thrones books, they're like fat, right? Because there's a bunch of pages. I don't know, some children's book, a lot thinner because there's fewer pages. And so in our example, the work's already been done, and our trend line has the equation Okay. Width hat is equal to 6.22 plus 0.0366 times pages. Okay, and then so what we'll do is if a book has 100 pages in it, we predict its width to be, well, we do 6.22 plus 0.0366 times 100, and we would get 6.22 plus 3.66, and what is that? 9.88. I think this was in millimeters. Okay, so we predict the width to be 9.88 millimeters. Okay, so that's just using the equation. I think I'm run out of time, so we'll have to finish this up on Wednesday. So we'll see you then, and good luck for your quiz today.